Vamos a empezar a emitir también en directo ahora.
Me ocupo de las admisiones, ¿no? Si quieres.
Por favor, sí, cualquiera de los que está en... Bien, bueno, voy a compartir mi pantalla, ya la ven. Ok, bueno, pues bienvenidos a todos, muy buenos días, gracias por levantarse de temprano. Estamos en la primera sesión de MACSS, que es la Mexican Cosmostatistics School, que como ustedes saben es parte de un evento más grande de la Universidad de Guanajuato, que es Mexicopas, el Mexican Cosmology Particles and String Schools. Y bueno, este evento lleva toda la semana, del 28 de junio hasta el 2 de julio, e incluso continúa la siguiente semana con la escuela de cuerdas. Entonces, bueno, ¿qué es? Vamos a empezar con una breve, perdón, se me saltaron varias diapositivas. Vamos a empezar con una breve como reseña de qué es MACSS. Entonces, es la Escuela Avanzada de Tópicos en Cosmología. Y en esta ocasión vamos a tener varios invitados, tanto para cursos plenarios como para las secciones de proyectos. Y pues bueno, le voy a pasar la palabra a Mariana para que ella nos hable más sobre MACSS, esta y las ediciones pasadas.
Bueno, pues aquí ven la lista que tenemos hoy de invitados. La idea un poco de MACSS siempre ha sido como tratar de vincularla con cosmología observacional. Eso es algo que hemos estado tratando de impulsar desde hace varios años. El tema que estamos viendo hoy, más o menos en MACSS, va a estar muy centrado en ver un poco la parte de estadística, en particular la parte de aprendizaje, de Machine Learning. Entonces tenemos en particular a la lecture de David Kirkby que nos va a dar, que junto con Miguel Aragón, que va a estar vinculado a un proyecto, y con Alberto Vázquez, que es parte de nuestro staff, van a estar vinculados a esta temática. Tenemos también una parte de charlas plenarias, que en este caso va a estar dado por dos chicas que tenemos aquí, Áñez Ferte, dos investigadoras del Jet Propulsory Laboratory California del Institute of Technology, y Elisa Chiari, que está en el Institute of Theoretical Physics of Utrecht University. Bueno, en la parte de proyectos vamos a tener a Simon Führer, que viene de Stanford University, que va a hablar sobre lensing. Entonces, como verán, estamos tratando de cubrir temas que tienen que ver con las grandes estructuras, con los sondeos presentes y futuros, como son pues TESI y LSST, que al final esta Alma nos va a dar una charla el viernes, igual plenaria, para poner todos estos temas, y estos son surveys que están pasando ahorita en primer plano, y ustedes vean las oportunidades de investigación que vienen los siguientes años. Alma. No sé si quieras comentar algo extra. Ups. Estás en mute.
Ay, perdón, es que no sé por qué se cambió la diapositiva. ¿Tú la cambiaste?
No.
Ah, ok.
No sé si quieras decir algo más de los invitados antes de que pasemos a la que sigue.
No, nada más los vamos a presentar también con un poquito más de detalle cuando ya, bueno, cuando sean sus sesiones en particular.
Ya creo que ya podemos pasar a la que sigue. Bueno, siempre hemos tenido, el plan de MACSS siempre ha sido tener una parte plenaria, bueno, como lecture, como curso, y una parte de proyecto. Entonces la idea es que en esta parte de proyectos siempre se les da a los estudiantes proyectos que puedan empezar y que puedan ir trabajando durante las sesiones, un poco ayudados por nuestros tutores, y en sus tiempos libres de forma independiente y autodidacta. Entonces, ese va a seguir siendo el formato, simplemente esta vez estamos pasando a un formato completamente virtual por la situación de la pandemia. Alma, si tú quieres, tómalo de aquí.
No, es que no sé, tal vez alguien más está viendo la presentación y por eso se está cambiando.
Ah, ok, bueno, sí, es que a lo mejor están tratando de adaptar lo que digo a lo que está puesto. Ajá, entonces justamente aquí vemos el horario. La primera parte es lo que les decía, la parte de las plenarias. Después tenemos los cursos en azulito cian, de Machine Learning, y después tenemos los proyectos en diferentes colores, ¿no? El Photo Redshift, el Machine Learning Basics con Alberto Vázquez y el Strong Lensing con Simon Birrer. Y el Neural Network con Miguel Aragón. Tenemos 4 opciones. Yo creo que tú ¿quieres explicar algo extra? Adelante. No. Ok.
No sé por qué no se cambia, perdón. Bueno, para finalizar, vamos a tener un par de eventos sociales. Uno es mañana a las 9 de la mañana en Zoom. Mañana sí empezamos a las 9. Y todos los demás días, durante el coffee break, esperamos verlos en el WonderMe, bueno, por ratitos, ¿no? WonderMe es una plataforma de interacción social un poco diferente a Zoom, en el sentido de que podemos hacer grupos de discusión. Ajá. Entonces, pues esperamos que participen allí. Recordarles que tenemos, bueno, que todos tienen acceso a otras partes de Mexicopas, ya sea la escuela básica intermedia o la sección de partículas o la de cuerdas, y la mayoría de las cosas, sobre todo cuando se traslapan con MACSS, van a estar siendo transmitidas en el canal de YouTube. Y bueno, también esto, quizás es la primera vez que lo escuchan, pero hay otro canal de Slack que es para todo Mexicopas, y ustedes pueden decidir si unirse a ese canal o solamente estar en el de MACSS, como ustedes quieran. Entonces les voy a hacer llegar también el link de invitación para ese otro Slack, y ya ustedes deciden si quieren unirse a él o no. No se los envié antes precisamente para no causar confusión y que primero se unieran al de MACSS. Entonces, bueno, voy a dar ahorita un pequeño break, 5 minutos, en lo que empezamos la primera sesión con nuestro invitado David Kirkby, que no sé si ya está en línea.
Antes, Alma, yo creo que podrías poner la presentación, porque se nos pasó entre la fase de las láminas todo el comité que de organización, creo.
Ah, sí, vale.
Si quieres, tú preséntalo, por favor.
Ok, para que nos conozcan, todos estamos ahorita en el Zoom. El comité organizador es Mariana Vargas Magaña, Gustavo Nisquevedo, si pueden prender su cámara y decir hola, Luis Ureña, Josué de Santiago y José Alberto Vázquez. Y pues bueno, por supuesto, como siempre, agradecemos todo el apoyo del Instituto Avanzado de Cosmología, de CONACYT, de la Dirección de Apoyo al Posgrado de Investigación de la UNAM, de la Universidad de Guanajuato, y por supuesto de la UNAM y del Instituto de Física y del CIMBESTAF en el apoyo para organizar este tipo de eventos.
Aquí se nos barrió.
¿Alguien?
Sí, nos faltó Sebastián Fromentó.
Ay, sí, perdón.
Bueno, también Sebastián Fromentó que diga hola. Gracias.
Gracias.
Ok. Y también si quieres volver a hacer como la parte de los proyectos, porque también la pasé muy rápido, porque...
Sí, dame un segundito.
Gracias.
Dame un segundito, déjenme cerrar una ventanita que tengo aquí abierta.
Digo, aprovechando que tenemos los 5 minutos.
Es que tengo una ventana abierta que no sé de dónde me está dando retroalimentación. Ok, los proyectos, entonces, ¿dónde
Las
están?
5. O temas.
Aquí están.
Ajá. Bueno, esto es lo que pasé muy rápido y sin la lámina, entonces es más fácil fijarlo cuando lo tienen en la pantalla. tenemos estos 4 proyectos. Como les decía, la parte de Machine Learning y Neural Networks, vamos a tener como 2 proyectos separados, uno más básico que va a llevar Alberto, que está aquí, y otro que más avanzado que va a llevar Miguel, que probablemente no esté aquí, pero va a venir el de Gravitational Lensing, que va a ser por Simón, y el de Photometric Redshift, que está aquí Sebastián. Y Bayesian Inference es el curso que todos van a llevar, y vamos a empezar en unos 2-3 minutos. Ya con esto yo creo que ahora sí ya cubrimos todos los temas. Alma, si quieres.
Sí, no sé si alguien tenga alguna pregunta o algo que quiera que aclaremos en estos 5 minutitos mientras llega nuestro primer invitado. Sí, hola.
Sí, hola.
Hola.
Hola, es algo que también preguntaron en el Slack sobre cómo nos van a asignar los proyectos, si nos lo harán como llegar por correo o nos dirán así o
Sí,
cómo va a ser.
muchas gracias. Sí, muy buena pregunta. Les mandé, si recuerdan, les mandé un archivo para que ustedes indicaran sus preferencias. Entonces, digamos, en la mayor cantidad posible vamos a respetar esa primera y segunda preferencia. Y lo único que vamos a hacer es crear los breakout rooms para que ustedes estén en los diferentes equipos. Y solo en el caso en el que para balancear el número de personas en los diferentes proyectos tengamos que hacer algunos movimientos, se los vamos a hacer saber y entonces en el mismo archivo vamos a hacer la modificación y lo vamos a resaltar en algún color o algo así para que ustedes lo tengan muy claro. Entonces, por ejemplo, hoy en la tarde tenemos 2 proyectos simultáneos, que es el de redshifts fotométricos y el de Machine Learning, digamos, el proyecto más básico de Machine Learning. Entonces, digamos, si su selección es tal que no hay ninguna interferencia entre estos o con la segunda, seguramente no habrá ningún problema. Ajá. Y nada más al momento de abrir el breakout room, pues asegúrense de que sí están en el correcto, de acuerdo al archivo que ustedes llenaron. En el caso, les recuerdo, en el caso de que haya alguna modificación para balancear el número de personas, se los vamos a hacer saber.
Ok, muchas gracias.
Respecto a los proyectos, por ahí surgía alguna otra duda que alguien me había hecho también, y era respecto a si podían trabajar con Google Collaboratory en lugar de tener instalado Python o alguna versión en particular de Python en su computadora. Esto va a depender de cada proyecto, ¿no? O sea, creo que, por ejemplo, el de Alberto Vázquez sí utiliza, de hecho, Google Colab. No estoy muy segura de Sebastián. La mayoría seguramente se van a poder seguir desde Google Colab, excepto que haya alguna librería que no sea fácilmente instalable desde allí, ¿no? Pero creo que la mayoría de las cosas sí se pueden hacer desde el Collaboratory. Y bueno, ahora voy a cambiar a inglés porque ya llegó
Nada más
nuestro...
un punto a notar rápido, que llenen el Google Docs, ¿no? Porque todavía veo lugares vacíos para hacer el horario en cuanto antes.
Sí, eso es lo más importante, que llenen el documento. Ok, y ahora sí voy a cambiar a inglés. Voy a dejar de compartir mi pantalla. So, hello everyone. So we are going to start with our first session of the day. There is a course given by David Kirkby, who has already joined the Zoom. So David, if you want to open your camera so we can see you. Hi. And so David Kirkby is going to give us a course on Bayesian inference and machine learning in cosmology. And this course is going to be 3 sessions, today, tomorrow, and after tomorrow, every day at the same time. And so we will, Professor David Kirkby is a professor in the Irvine University of California. and sorry, University of California, Irvine, UCI. And he's a collaborator of some of us in DESI as well as in the LSST. So without more delay, I think I can pass the floor to you. Thank you, David.
Thank you. Hello. I'm David Kirkby. I think you need to let me share the screen. I can't do that. And I'm going to put a link to the my slides for this morning in the chat.
You should be able to do it now.
Okay. And so I'll keep the chat open, and people are welcome to either put questions in the chat or just to interrupt. But it probably, if someone else could watch the chat and then just put interrupt if there's questions, because it's pretty hard for me to watch the chat. I don't have enough screens. So okay, so but I mean, questions are great. I'd love to have questions and answer them, but it's hard for me to see them also. Okay, so you see my title slide?
Yes.
Great. Okay, so for today, I'm going to start with just a general introduction to machine learning in astronomy. And so really going to start from the kind of the high level view, sort of the 20,000 foot view of machine learning. But this is going to be I'm going to be talking about what it's like to do machine learning specifically in the context of science and astronomy in particular, because although there's a lot of work going on in machine learning in industry, there's some important ways that as scientists, we really have different needs and different expectations for what machine learning can do. So although it's very easy to find lots of examples of classifying dogs and cats and things like that online, you have to be a little careful in how you adapt that stuff for use in a scientific application. So that's going to kind of be a theme for today. How, as scientists, are we going to use machine learning differently than people are doing in companies like Google and Facebook? So to get started, so what do I mean by machine learning? And there's many different ways of defining it. I prefer a fairly broad kind of open interpretation. And so first of all, in machine learning, so it has the words machines in it. So we're using machines somehow. And what we're doing, really the activity of machine learning is we're learning how to explain data with models. Okay, so data and models are two core components of machine learning. And I'm going to focus on those today, but let's just talk about the machines first. So what really are the machines that give us most of the progress in machine learning? So they're not things with gears, traditional machines. There's really three things that you could call machines. There's software algorithms. So and so a lot of the progress in machine learning, in particular the modern so-called deep learning era, has really been enabled by a new class of algorithms. So basically theoretical developments, coming up with new algorithms. A second important type of machine that enables modern machine learning are modern computer hardware architectures. And in particular, all the development in GPUs, or graphical processor units, which were originally designed to make games, 3D video games, go faster, but have now really been adapted to, since the underlying linear algebra calculations that they do are also really the core numerical work of machine learning. Those architectures have really been an enabling technology. So they're really also an important type of machine. But then finally, maybe the most important machine is just humans in the loop. So it's really human ingenuity which has come up with the software algorithms, figured out how to take this hardware, which was meant for games, and to leverage it for doing machine learning. So really a lot of the advances are coming from this human ingenuity. So those are the machines in machine learning. Okay, so we're using machines to learn. So what do we mean by learn here? So really, machine learning is a very shallow type of learning. Although we always use the term deep to describe machine learning, the actual learning that's going on is very shallow. And what I mean by that is that really what the learning involves is it's just identifying statistical correlations in the data. And it does this in a very passive way. Basically, you feed a lot of data into an algorithm and it just analyzes it and then just picks out statistical correlations. And that's what the learning involves. And what I mean by passive is to think about how you learn about your environment and learn about the world. And you do that by actively engaging with the environment. You actually experiment and you identify causal relationships. So in machine learning, how do you teach a computer about gravity? You can show it lots of balls falling in movies, say, and eventually, an algorithm will learn that when a ball is not being held by something, it's going to fall and it's going to have a particular acceleration. But what you would do is, you would just pick something up off a table and you'd let go, right? So you're basically generating the data when you do your own, when we learn as humans, and machines don't do that. So it's a very passive way of learning. And also passively, you can't really identify, you can't have a theory, which is, you develop a theory, if I pick this object up and let go, that it's going to fall, and you can just test that theory. And an algorithm can't do that. Okay, so we're using machines to learn how to explain data with models. So they're really the core pieces of machine learning are the data, that's the data that you're going to provide, and then the model that you're going to select to explain your data. Okay, so let's look at a bit more concrete example. I'm going to show you in just some high-level diagrams the cycle of machine learning, and we'll talk later on that there's really different flavors of machine learning. So here specifically, I'm talking about supervised machine learning. Okay, so already right here we see the data in this box up here, and here's the learning process, or practitioners often call that training. And our data in the supervised learning context our data is split into two pieces. There's all the features that we want to identify the patterns in, and then there's some targets, true values, or what are often called labels. And so what we're doing is we're feeding our data and the true labels into some learning process, and that learning process is guided by some model, which at this point is kind of a vague thing. I've kind of got it in this cloud here. And then, so that's the learning phase in blue. And then we have a second phase, which is the prediction phase, or what's sometimes called the inference phase. And the inference phase looks very similar. We feed in data, but now it's just the features. And instead of feeding in the labels on the left, which is the desired answers, what we do is the prediction phase generates labels. So these are predicted labels. Okay, so they have the same structure. Like if our data consists of photographs and we're trying to identify cats and dogs, and the labels would be, is this a cat, is this a dog? And in one case, we have the true values, we feed those into the training. And down here, we're predicting those values. So that's the second phase in green. And notice we have the same model that's supervising this whole process, okay? In the learning phase, where we're basically learning the internal details of that model, And then in the prediction phase, we're turning around and having the model generate predictions, but it's the same model. And then finally, the last stage is to assess how well we've done. We've done the learning in blue, the prediction in green, and then finally we want to assess. We want to say, how well did we do in those predicted labels? And in order to answer that question, we have to now know the true labels for that data that we used in the down below for the prediction. Okay, we didn't use them for a prediction phase. We didn't train on those true labels, but we have to know those in order to do this, this assessment phase. Okay, so that's sort of a high-level picture in diagrams. But now let's actually do this in a more concrete way. So I want you to be the machine learning algorithms. And so I'm going to walk you through an exercise where you actually do these steps yourself. Okay, so what is the data that we're going to work with? So the data are some astronomical images. So you see examples over here on the right. So what are these images? So these are small postage stamps, close-ups on the sky of galaxies. And you can see that this is actually simulated data. It's extremely high signal to noise. You don't see any fluctuations in the background here. So it's kind of an idealized problem, but it's already quite tricky. And the label, okay, the thing that so the data are the images, basically the pixel values that you see here. That's the data. The labels are the number of galaxies that are in each of these postage stamps. Okay, so this one on the top left has one galaxy. So this is image number 13, and it contains one galaxy, one galaxy, one galaxy. Over here, so this one here contains 3 galaxies. This one in the top right, number 18, has 2 galaxies. Okay, so it's not obvious just taking a quick look at this to determine the number of galaxies in the image, but that's exactly the task that we're trying to do here. So we need a model that can be trained on this data. So basically, we're just going to feed in these pixel values plus the true labels, the true number of galaxies in each one of these images. And so we want to learn to predict the number of galaxies in an image when you don't know the answer. Okay, so any questions about what the problem is, the task here that we're trying to do? Okay, so now what I want you to do is to do this yourself. So so that link, if you put in this short link, so I want you to actually try doing this yourself. And I've got 12 images over here. So now we're doing the green phase. The green data is these images on the left. And so I want you to train yourself on the data on the right, and then try and predict the values on try and predict the number of galaxies in each one of these 12 images. And if you go to that link, there's a form where you can enter your predictions. I'm just going to, I'll paste that link into.
I think Gustavo already did.
Someone pasted the link? Okay, thank you. I think I messed it up. Okay, so while you're working on this, I'm going to get my screen sorted out again. Yeah, so just take a few minutes, look at look carefully at the training data. So those examples, those 36 examples, and then try and predict for each of the 12 which are unlabeled what the true number of galaxies is. Okay, so just a few more seconds, and then we'll talk about the results here. Okay, so number one, the one in the top left here, you can see my slides again. Is that right? Yes.
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 Okay, great.
Yes.
Okay, so number one, looking at this, probably not one galaxy. Now, how many galaxies is it?
I think it is one galaxy.
You think it's one?
Yeah, I think so.
Could be, yeah. I mean, there's certainly kind of it's one blob. Mariana thinks it's 3. Andrea thinks it's 3. Yeah. It's pretty hard to tell, though, right? Okay, so but maybe there's some confirmation bias. When someone says it's 3, then everyone says it's 3. Okay, so let me show you some results here. So when I've used this survey before, so I already have, your results aren't included yet, but next time they will be included in the green histogram. So what I'm showing here is for each of those 12 examples, the true answer is the red line. So you were right, that first one is 3. The green histogram shows you the distribution of answers that humans have given for this problem. And then the blue histogram shows what a deep neural network trained on the same data achieves. Okay, so basically what you have done quite quickly, you did it a lot faster than it would take to write the neural network model and do all the training. But we're getting similar results. So really, what's one of the things that's striking here is that a relatively straightforward neural network can basically get close to human performance on a problem like this. Okay, so what we're doing here is looking at this graph is we're doing that assessment phase, because we're now comparing what a human or an algorithm predicts by bringing in the true labels, which are the red lines here. Okay, so there are some surprises. So let's see, probably the most striking is this one over here, number 11, down in the corner. So the true answer is 3. Okay, so but both humans and neural networks are pretty confident that the true answer is 2. So this is just a case where it really is ambiguous. The cues, the information that's provided in the data really suggests 2, but there is a statistical distribution, and in this case, the true answer happens to be 3. And that's okay, because if we look at these histograms, then although maybe 80% of the time, so basically what do these histograms mean? They mean that we're 80% sure that it's 2 and 20% likely that it's 3. And so, so that this should happen about 20% of the time, then the real answer will be 3. And so we're only seeing one example out of these 12 where it's kind of where the most probable answer isn't the correct answer. There's also, it's interesting to see that in general, the neural network is a lot more confident than we are as humans. So if we look down in these examples over here, number 7 and number 8, see that the neural network is pretty sure that that's 1 in both cases, and that's actually the right answer. Whereas humans were more uncertain and said there was a larger probability that the answer was actually 2. Okay, so hopefully by actually going through and doing this exercise yourself, now you have a pretty concrete understanding of what's going on in this supervised learning loop, where you first train by looking at the examples, and then you go through the prediction phase, and then finally here in the third phase, we compare the predictions to the true labels for that data. Okay, so I didn't show you, the details of the neural network algorithm that was used, but I think you're going to get separately lectures on neural networks, and so what I used here is just a pretty straightforward dense neural network, and the input to that neural network was really literally the pixel values, so no processing on the data to try and extract features like centroids and second moments or ellipticities and anything like that. Really just feeding in the raw pixels. And so it's pretty impressive that an algorithm can match human performance, and that happens quite a lot. There's a lot of areas where algorithms are able to match human performance and often do better than human performance. In fact, one of the one of the limitations in doing better than human performance is that we don't have labels. Often the labels are human generated, and so you can't, if you're training on human labels, you're never going to be able to do better than human performance. Okay, but here's a really important difference, is that when you did this problem, you were able to generalize from only 36 examples. Basically, you only saw that one page of labeled examples. But a neural network, in order to get the same performance with the neural network, so I have to show it tens of thousands of labeled examples. Okay, so there's a huge data set that I fed it, and I didn't just show it to them once. That would be called one epoch. I had to show it hundreds of times. So it had to go through those 10,000 examples 100 times before it got that level of performance. Okay, so do you think you would have done better if I had given you, instead of just one page of examples like this, I gave you one page of examples. If I'd given you 100 pages of examples, would it have really helped much? I don't think so. It wouldn't help me, because the problem is that we're very good at taking a small amount of data and kind of synthesizing a model. So basically, building this model, whatever's in the cloud here, we can do that very quickly with a small amount of data. In machine learning, that's called one-shot or few-shot learning, where basically you need very few examples to quickly learn something about the data. And most algorithms are very poor at that. If they have a small amount of data, they learn almost nothing. But the difference is that the computer never gets tired. You would get pretty tired of this after looking at second or third page. And if I gave you 1,000 pages, you would just you'd shut down after the first few pages and stop learning anything new. Okay, but the computer is the opposite. It learns very little from each example, but it never gets tired, and you can feed it thousands and thousands of pages of training data, and it keeps on getting better and better. Okay, so that's important to remember. Although we talk about machine learning, and we have the word learning in there, that this is really something fundamentally different from how we learn. And one of the consequences of that is that you need, if you want to do any kind of learning algorithmically, you need to have huge amounts of data. Okay, you might be able to get to human performance, but the way you're going to get there is fundamentally different from how humans learn. Okay, so modern machine learning, although we call it very deep, in many ways it is very shallow. You're going to need huge amounts of data, and it uses it very inefficiently, and that can be quite painful when our data is hard to come by. So how does the machine learning algorithm actually see your data? So first of all, what do we mean by data in the most general sense? So it's basically just a finite set of measurements. And in general, machine learning algorithms take a very kind of uniform view of data. They don't care about any of the details. You basically have to coerce your data into just a two-dimensional spreadsheet. So in astronomy, we're used to working with FITS files, where your data is spread over many FITS files. Each FITS file has different HDUs. So in DESI, our kind of basic unit of data is something where there's a table of wavelengths, and we have resolution. At each wavelength bin, we have a resolution. We have fluxes. We have inverse variances. We have pixel masks saying which pixels were hit by cosmic rays. So it's a fairly rich, complex data structure. And in particle physics is even worse. They use these things called root trees, which are kind of hierarchical trees to represent each observation or event that's collected. But to use any of the modern machine learning algorithms, you have to force your data. You have to sort of flatten it out into this two-dimensional table format. So it's basically just a spreadsheet. You've got to turn your data into a spreadsheet. And by convention, we normally make the rows of the spreadsheet are the different observations or samples, and then the columns are the different attributes of one observation. And machine learning, those are known as features. And so, although our scientific data, and especially in astronomy, tends to be a lot richer, you have to you're going to have to flatten your data out to use machine learning algorithms. And another issue is that you may have to truncate your data or pad your data. So you have to have the same. So for example, if we're looking at spectra, there's different lines that you can identify. So one spectrum might have 2 clearly identified lines, and another one would have 4 clearly identified lines. Okay, but that's the number of features has to be the same for every observation. So you're either going to have to say every observation has 4 lines, and if I'm missing 2, then I'll just have to put in zeros, and that could cause problems. And if I have another spectrum which has 6 lines, then I'm going to have to pick the best 4 and throw away the other 2, so potentially losing information. So you have to make some sacrifices and choose some trade-offs in order to coerce your data into this sort of spreadsheet view. There's really only 2 areas in machine learning where there are kind of now specialized algorithms that can handle data in a more natural format. So one is in images. So there's a lot. Images it's a 2-dimensional array of pixels, and each pixel is really three numbers. There's a red, a green, and a blue channel. So there are a lot of algorithms now that can handle that format directly, and that can actually be useful for for astronomy, where we do work with images a lot. And then another example is text. So there's a lot of machine learning algorithms are focused on processing just natural language. So for example, a classic machine learning problem would be translating from Spanish to English, for example. And so there are algorithms that can just work literally with a sentence in Spanish and a sentence in English and transform one to another. So those are kind of the two areas in machine learning where you aren't forced to use this spreadsheet view of your data. Okay, so once you've forced your data into this spreadsheet format, so then there's some questions you need to start asking about your data. So each one of your columns, what I called features, what type of column is it? Is it categorical, or is it discrete or continuous? So what do I mean by that? So a continuous feature would be something that's basically represented in Python with a float. Okay, so like a wavelength or a flux. Discrete data would be something that has that at least conceptually has some sort of integer value. So if you have a sequence of lines, then you might have an index associated with each line in a spectrum. And categorical data would be something which where you basically have a kind of a text description of the different possible values. So there's a finite set of values. So for example, in a spectrum, it might be a good spectrum, a bad spectrum, or we're not sure. So you'd have three categories. So in general, interesting data sets are going to mix all 3 of those types of features. So that can be a challenge for machine learning. But it's important you know what each type of feature is. Oh yeah, so Braulio asks, is categorical equivalent to discrete? So there is an important distinction there. So discrete implies that you could map the different values to integers, and that so in particular there's an ordering to there's a natural ordering. So you can say that 0 is less than 1 is less than less than 2, but categorical would be like red, green, and blue. So there's no natural ordering to those. So yeah, that's a good question. Okay, so that's kind of the different flavors of features that you can have. And what about the samples? So if I was to shuffle all the rows of my data set, would that make any difference? Or is the ordering of the rows significant somehow? So, a common case where the ordering is significant is if you've got a time series. So let's say we're measuring a light curve for a supernova. So you've got a sequence of flux measurements over time. And so in that case, of course, the ordering is important. In general, machine learning algorithms assume that the ordering doesn't matter. Most algorithms cannot handle time series. And so that's sort of a specialized area of machine learning to deal specifically with time series. But most of the algorithms that you'll come across really assume fundamentally that there's no intrinsic ordering to the rows of your data set. Another built-in assumption in a lot of algorithms is that all of your rows are statistically independent. Okay, so that means that fundamentally, we're going to talk more about the underlying probability and statistics assumptions later on. But basically, what you're assuming is that all of your observations are basically random numbers generated from the same underlying an unknown probability density. Okay, so that's one of the implications of that is that you can shuffle them because your random numbers can come out in any order. But often with scientific data, this assumption is broken in kind of subtle ways. So, for example, if you're collecting data with a telescope, then you might have so DESI is going to shut down for the summer. We're going to take out we're going to disassemble the focal plane and put it back together with some updates to the electronics. So is that to some extent we've now rebuilt a new instrument? So is the data that's taken after the shutdown, is it really drawn from the same distribution as the data taken before the shutdown? Or what about the data that we collected during our kind of commissioning and survey validation phases? Can we combine that with the data that's taken in the main survey? Okay, so you have to think carefully about these issues, because a lot of machine learning algorithms really assume that they're not expecting the data to have different kind of chunks with different properties. And so if you've got the data after a certain point is really somehow different than the data before a certain point, maybe you change your quasar selection algorithm, for example, you can always analyze the two separately. I mean, that's it's not a it's not fatal if you do have those breaks, but you may have to just split your data and analyze it in separate chunks. What are the uncertainties in your measurements? So when you have these continuous variables, so you might have a flux. Well, what's the uncertainty in that flux? And one of the things that's kind of unique about scientific data is that we often actually have a pretty good idea of the uncertainties, right? So we have, generally, whether we're collecting imaging data or spectra, for every pixel of information, we already have an estimate from the pipeline of what the uncertainty is, and usually expressed as an inverse variance, 1/sigma squared. But how should you handle those uncertainties? So one thing you could do is if you've measured a flux, you could take the error on that flux, or the inverse variance, and treat that as a separate feature. So that's one approach. It becomes quite expensive because then you double the number of features that you're working with. But that's kind of an open problem in what's the right way to use scientific data where uncertainties with these machine learning algorithms. What do you actually do with the uncertainties? And if all the uncertainties are basically the same, like if all of your data, all of your observations have essentially the same signal to noise, then there's really just one number that describes the uncertainty, and a machine learning algorithm will generally learn to work with that signal to noise. But what's more common is that your data has quite a big spread in signal to noise. So you might have, one day you'll have some observations where the seeing was very poor or the sky was very bright, and you have low signal to noise, and on another day you have much better signal to noise. And in order to optimally use that data, it's important to weight the different observations by their known signal to noise. So another question about your data is whether your data is binned or unbinned. Okay, so are you just measuring individual events in your data, or have you somehow binned events together? So, for example, a CCD collecting photons, the fundamental events are photons arriving, hitting the primary mirror and passing into your instrument. But generally, we don't record individual photons. We bin them into pixels, and we also bin them in time. Right? We collect all of the photons hitting one pixel, so that's one piece, a little bit of solid angle on the sky over an exposure time. So we bin both in angles on the sky and in time. But sometimes you have, when we look at another type of data that we collect with telescopes, is telemetry data. So the temperature of the focal plane or of the primary mirror, which often correlates in subtle ways with the things we're interested in and leads to systematics that we need to study. So those aren't binned though. Those are really measurements, individual measurements that we collect. So we have to think about which features in our data represent some binning and which are unbinned. And then another subtle point is if you take a whole sample, so one row of your data set, is there a natural distance measure on your samples? So now imagine if I take two separate observations, two rows of this data set, how can I measure how similar or different those two observations are? So that's quite a difficult problem in general. So if everything was dimensionless, or if everything had the same dimensions, let's say our features were just X, Y, and Z coordinates in space. As long as X, Y, and Z are measured in the same units, microns or meters or megaparsecs, then there's a natural way of saying how similar two sets of X, Y, Z are. We just take the Euclidean distance between them. But what if, in addition to X, Y, and Z, now we have an energy or a temperature? We add an energy or a temperature feature to our data set. So now how do we can't really just extend the Euclidean distance to combine meters and degrees Kelvin and electron volts, right? Because there's no natural way to compare things in different units. And so why does this matter? A lot of machine learning algorithms, especially unsupervised machine learning algorithms, the way that they learn patterns in your data is with basically by using a Euclidean distance between your samples. But unless all your features are very homogeneous, so they're really measuring the same thing, and a Euclidean distance makes sense, it's going to give you wrong answers. So. And often the way we have to deal with this, if we want to use algorithms like clustering or dimensionality reduction algorithms, you have to pre-process your data and really into a form where you can just take the Euclidean distance between any two samples, and it is a meaningful measure of how similar two samples are. Okay, so as scientists, we tend to think that our data is really precious, and that's because we put a lot of effort thinking about how we're going to collect the data. We put a lot of effort. We take shifts to record the data. We build wonderful instruments, like this one on the right here. But let's contrast that with where the data comes from that's mostly used in industry. So where does data come from? So mostly the data that's used in industry is generated by you when you're spending time online. So for example, a pretty important type of data in industry for companies like Google and Facebook is ads. And so whenever you click on things, in a web page or in Facebook, you're generating data. Okay, when you do a Google search, and like let's say you do an image search, then you're basically providing labeled data. If you search for poodles, and it's going to show you a bunch of images, and then the first one you click on, so it now has learned that image is is well labeled by the thing you searched for, a poodle. Okay, so most of the data is sort of you get in industry. Most of the data essentially comes for free. Data is really cheap. There's a lot of data available, but for us, it's really the opposite. Data is not cheap. Data is expensive and it's precious. Okay, so scientific data really is fundamentally different from a lot of the data that's used in industry. Like just clicks in your browser on ads. And what that means is a lot of modern machine learning methods don't really recognize or take advantage of some of the kind of unique features of scientific data. So in particular, I think there's 2 points that are important. So one is we're not just consumers of data. Okay, Google doesn't really generate data; they consume data that you generate as you use the internet. Okay, but we are fundamentally data producers. Okay, we do really the whole life cycle of the data. We design the experiment, we design the instrument, we run the instrument, we do the quality, the QA on the data. So we really produce the data. We think carefully about how to make trade-offs. How are we going to optimize and trade off statistical and systematic uncertainty? So a whole host of issues that people never really think about in industry. And the other way that our data is quite different in astronomy is that our data is fundamentally measuring underlying physical processes. Okay, so most fundamentally in optical astronomy, we're just collecting where our events are recording visible light photons. And we understand, the underlying quantum statistics of photon collection. I mean, counting photons is very well described as a Poisson process, just from first principles. And also because our data originates from physical processes, we have dimensions and units that are important. But most machine learning algorithms don't know anything about data about units. Right? If you work with Panda to represent your data, it's a very powerful tool for processing data, but it doesn't know anything about units. And so if you ask Pandas to take the ratio, to make a new column that's a ratio of 2 existing columns, then it doesn't, let's say you want to add 2 columns together to make a new feature. So if one of your columns had units was in wavelength in angstroms, and another column was energy in electron volts. Okay, it doesn't make sense scientifically to add those 2 things together, but Pandas isn't going to care. Okay, so I have some homework for you for tomorrow. So I've kind of given you a high-level overview of how data works, but I want tomorrow we're going to actually do some exercises with some data, and I want you each to select a data set to work with in tomorrow's session. So it can really be anything. It can be related to your research or hobbies or anything that you're interested in. And so the two, what type of data is acceptable? So there's really just 2 numbers that describe your data set. And so remember, we're thinking of data as just a spreadsheet. So it needs to fit into that spreadsheet format. And then it's just how many rows do you have, n, the number of samples or rows. And so I want you to pick a data set that has at least 100 rows. And then how many features does it have, or D, the dimensionality of your data, the number of columns. And so aim for something with 10 or more features. And if you're kind of going on the high end and you've got lots of data, then try and keep the product of these, so the total number of cells in your spreadsheet, n times D, to be less than 100,000. And if you need to, just trim trim rows or columns to get under that. So it doesn't really matter the shape. The proportions between entity aren't too important. And any format is okay as long as it can be imported into pandas, because we'll start by looking at working with the data in pandas. And then a good source, if you're wondering where, like, let's say you've been spending a lot of time on Netflix and you want to find some data that would be related to Netflix shows that would be interesting to study, then a good source for any, there's a huge amount of public data that's available at this link right here, kaggle.com/datasets. And so that's a good starting point there. So if they have a search bar, if you type Netflix there, you'll find tens of data sets related to Netflix there. So. Okay, so it doesn't have to, I mean, you're welcome to use something related to your research, but it should just be something, some data that you're interested in and have some, you have some sort of expert domain knowledge about the data, either because you spent a lot of time on Netflix or because it's related to your research or your interests. Any questions about that? And I think I just want to just stop for a minute and just generally see if people have questions at this point.
There was a question in the chat, so probably you cannot read it. So it was a question from Raulio Morales Martinez, which has who asked if categorical is equivalent to discrete. So probably for the classification problem.
So yeah, I think I answered that earlier when I saw that.
I'm sorry.
Was that okay earlier? What I said?
Oh, it's okay. You already answered. Thanks.
Okay, so I want you to just to start thinking now about. Oh yes, Maribel asked, the data could be Excel. Yeah, because pandas can read Excel. So, and what we're going to do, actually, what we're going to do is we'll look at it a little bit in Python, then we're going to export it into CSV and use another tool to look at it. And if you've never used pandas before, don't worry. It's a good investment of your time to learn. It's really kind of one of the main tools for people working in data science. But it's quite similar. Maybe another. It's roughly equivalent to the tables in AstroPy if you're more familiar with those. The one thing that pandas can't handle is FITS files. So. Okay, so we've been talking about data. Remember, data is one of the two main components of machine learning, and the other is models. And now we're going to talk more about models. So all machine learning algorithms use a model to explain your data. Okay, it's not always obvious when you're reading about neural networks and you're kind of looking at all of this code in TensorFlow or PyTorch. It doesn't really seem like there's a model. We kind of think of a model as a mathematical abstraction, and that just looks like a lot of code and arrays and tensors. But really, fundamentally, all machine learning algorithms use a model. It doesn't matter whether they're supervised or unsupervised. And I mean model here in a pretty broad sense. So, for example, Markov chain Monte Carlo can be thought of as a model. It's something we use in inference, especially for cosmology. So what is a model doing? So a model is, remember that we're learning a model to explain your data. How does the model explain your data? Internally, it has a whole bunch of knobs that can turn parameters. So those knobs are just parameters, and in learning just consists of tuning all of those parameters to best explain your data. So you can I like to think of one of those big mixing soundboards with all the knobs and sliders. And so you hand there's someone sitting there at that with this big control panel, and you hand them a bunch of data, and they just kind of keep going through the data many times. And each time they're turning the knobs and adjusting the sliders, until they get the best possible explanation of your data. Okay, so what do we mean by best explaining your data? So there has to be some sort of metric, some number that says how well you've explained the data. Okay, so that's another, for actually doing machine learning, you need a model, but independent, which is one sort of mathematical abstraction, but you also need some metric, some number that compares the model's predictions with the true values, the true labels for the data. And so there's another mathematical object, the metric, or often called the loss function, that's required. So how important are the parameters compared to the model itself? Okay, they're not separate. A model has parameters. Okay, a model is basically a collection of parameters, or a model is governed by the settings of its parameters. But the relative importance of the model itself, kind of the mathematical abstraction, and the parameters, which are numbers, it really depends on the task that you're trying to accomplish with machine learning. So, I've listed here 3 tasks, which kind of differ in how important the parameters relative to the model are. So the first is to estimate the cosmic sound horizon. So basically to make a BAO measurement, baryon acoustic oscillation. So this is something that you could use machine learning for. And in this case here, it's really the parameters of what we're interested in. Okay, think of the paper that we're going to write. So what are we going to put in the paper? We're not going to put all the details of the model in the abstract. We're going to put the values of the parameters. Okay, so that's fundamentally it's really mostly about the parameters. There is still, of course, there is a model, right? We have the fitting program and all the modeling of the spectra used for the redshift estimations, but it's really the parameters at the end of the day that are important. If we look at the other end of the spectrum, so down the third example, identify pixels with cosmic ray. Okay, so this is something, before we can do any analysis of our data, whether it's imaging data or spectroscopic data, there's some low-level instrumental stuff that we have to deal with. And so cosmic rays are one of the facts of life for a CCD on a telescope, generally because they're either in space or on the top of a mountain where there are a lot of cosmic rays. And so machine learning is actually really good at identifying pixels in the raw data that have cosmic rays. And the models that can tell whether a pixel is just nice photons from extragalactic photons, or whether it's just excess charge from an ionizing cosmic ray, the model has lots of parameters, but the values of those parameters are totally uninteresting. We don't care about the parameters of that model. What we care about is the model itself, because the model itself lets us, once we've trained that model, then we can bring new raw data tomorrow, and we can identify which are the pixels that we need to mask out because they're hit with cosmic rays. So the first case is all about the parameters. The last case is all about the model. What we want is a model that can predict which parameters have cosmic rays in it. And then in the middle, I've got an example which is somewhere in between. So the middle case, we care somewhat about the parameters, and we also care, though, somewhat about the model. So the middle task is the one that I had you do earlier, where you have a small postage stamp image, and you're trying to estimate the number of galaxies present in the image. Certainly, the parameters, the model is important because we want to be able to predict in new data whether we're looking at a blend of 2 galaxies, which for weak lensing is really important, because weak lensing is we generally assume that when we measure the shape of some region of pixels on the sky, that we're really measuring the shape of an object at a single redshift. So when that's not true, when we have blended galaxies at different redshifts, we need to know that. But the parameters are also interesting, because the parameters are actually telling you something about the population of galaxies. Because in order to do that problem, you have to have some notion of like what a single galaxy looks like. What's the range of sizes and shapes and colors, morphologies of galaxies. So the parameters are also interesting there. So that's sort of on the interface where we're interested both in the parameters and the models. But the important thing I think to remember is that it's not either or. Okay, there's always a model and there's always parameters. A model always has parameters. If it didn't have any parameters, it would have no capacity to learn, because learning is all about adjusting those parameters. Okay, if you had a big soundboard that just had an on-off button, that would not be very useful. You couldn't learn anything from that. There's no settings. And in scientific applications of machine learning, when the parameters are interesting, then it's really important and interesting to also say something about the uncertainties on those parameters. And so, although you can imagine, using quite a number of machine learning approaches where you could just spit in a whole bunch of raw data and it would just spit out the BAO scale. It'll say alpha perpendicular is 1.01. But unless you have an uncertainty on that number, that's not very useful. And it's actually quite difficult to get reliable, interpretable uncertainties out of most machine learning algorithms. So that's we need to, as astronomers, we need to be aware of what are the challenges. It's not just enough to get a number out, an answer. We also need to have a pretty good idea of the uncertainty if it's a parameter we care about. Okay, so where I'm going with this is there's really one process. We've got data, this triangle here, we've got data on the left, and then on the right-hand side, I split into a model in the upper corner, in the upper right, and parameters down below. But they're like different sides of the same coin. You have the model, the actual kind of a mathematical abstraction or the code, and then you have the parameters, which are the numbers that determine exactly what the predictions are going to be. And so kind of what is the process that flows from data to models or parameters? So the data has some patterns in it. What do I mean by that? So, I mean, what's an example of data with no patterns? It's something that's just generated by a random number generator. So, okay, truly random data has no patterns, and then there's nothing you can possibly learn from it. It has maximum entropy. Once you're starting to find patterns in the data, then there's really two different two different ways of building on those patterns. You can either train a model to learn those patterns. And once you've done that, then really what you're saying by talking about training a model on the data, that implies that the activities, what you want to do in the future is you want to be able to generalize the data you've already seen to either generate new data or to predict labels on new data. So really the product, if you take this path here, you take the patterns in the data and you train the model, then what you're doing is you're saying, really what I'm interested in is being able to apply this to new data that I haven't seen yet. But the other path you can take is you can take the patterns that you find in your data, and then you can fit the data to get the parameters out. Okay, so here, what you're not mostly interested in being able to make predictions with new data. You've got all the data you're going to get. So let's say we've got the first year of data from the Rubin Observatory or from DESI. So we've got a well-defined data set, and we're not trying to predict the next year's data set. We just want to work with the data we've got, and we want to quantify the data we've got, and we want to interpret it. And so there, basically, the activity we're doing is fitting. Okay, so although we often think of these as very different activities, fitting and training, really they're just two different aspects of the same thing. In both cases, you have a model and you have parameters. The only difference is really what you're most interested in. Are you most interested in the model that comes out because it can now generalize and predict new data? Or are you interested in the parameters that come out and their uncertainties, because that lets you say something about the data you've already collected and write papers. So there's different fields that kind of focus on different areas of this triangle. So data science, when people talk about data science, really what that's spending your time mostly quite close to the data. So you spend a lot of time in data science just collecting the data, getting it into a consistent format, cleaning the data. You're dealing with those issues that a lot of data doesn't naturally fit into this kind of spreadsheet rows and columns view. You might have data where you have missing observations, or you have some invalid data, or you have data taken last year is somehow different than the data taken this year. So there's a lot of work in just really fundamentally dealing with the data, and then starting to see patterns. So that's really the domain of data science over here on this left-hand side. Traditionally, when people talk about machine learning, really what they're focusing on is in this upper path, where we're mostly interested in training a model that can generalize and predict new data. When we take the lower path, so that's normally what people think of as statistics, where we're quantifying or interpreting our data. Okay, so with this kind of broad viewpoint, when we do things which are traditional statistics, estimating parameters using chi-squared or maximum likelihood or Markov chain Monte Carlo, so that really is a form of machine learning. It's just that we're focusing more on the parameters that we get out rather than the model we end up with. Yes, that's a pretty broad view of machine learning, but I don't think you can draw a sharp line and say, this is machine learning and this is statistics. There's really a very smooth continuum between these, depending on how important the model is to relative to the parameters that come out. So this is a kind of a humorous comparison that someone made a while ago, comparing machine learning, the kind of people who call themselves machine learning researchers on the left and people who work in statistics departments on the right. And the point this is making is that there really is a one-to-one correspondence between concepts in machine learning. Like in machine learning, we talk about weights, and in statistics they call those parameters, right? The weights in the parameters of machine learning really are just weights. In machine learning, we talk about learning. On the statistics side, we talk about fitting, generalization, test set performance. So there's really a one-to-one correspondence between the concepts of these things, and they really are just the same activity, just with a different emphasis. Some practical differences is that a large grant in machine learning would be in the millions of dollars, whereas a large grant for someone in the statistics department, it's much smaller, $50,000. Okay, they also have much fancier meetings in machine learning conferences than we do in statistics. So, in Vera Rubin Observatory, which I've been a member of a while, we have our annual all hands collaboration meeting. It's always in Tucson in August. So it's a nice hotel, but extremely hot outside. So that's why no one else wants to be there. Okay, so I've talked about models and parameters. Something else you'll hear about are hyperparameters, and they play an important role in this. So what's the difference between a hyperparameter and parameter? From the name, you can tell they're obviously related to each other. A hyperparameter is really, it's another knob or a slider, like on that big soundboard. But the distinction, the key difference between a parameter and a hyperparameter is that you learn the parameters from the data, and the hyperparameters are all the settings that you don't learn from the data. Okay, so that's really just a definition. And sometimes you have a choice, a particular knob, you can either choose to learn it from the data or not. Okay, so it's not, it's not that one number is always a parameter or a hyperparameter. It will depend on the algorithm you're doing and your choice in how you're going to use the algorithm. But there are always going to be hyperparameters. There are always going to be some things that affect the answers, but which aren't going to be learned from the data. Okay, so you have two choices. You either have to set these by hand, and that's generally very easy to do, but it's also a very biased procedure, because if you're just arbitrarily setting something by hand that can affect the final results, as scientists, we have to be worried about to what extent is our final results dependent on those. Okay, yeah. So Louis asked for an example of a hyperparameter. So let's take clustering for example. So let's say I've got a bunch of points in 2 dimensions, and I want to I've got kind of a cloud of points, and I want to say how many clusters are present in that data. So maybe is it sort of one cloud of points, or are there two separated clouds of points, or three clouds of points? So there's a bunch of so-called clustering algorithms. There's a lot of them implemented in a package called scikit-learn. But when you use those clustering algorithms, a common feature is none of the algorithms let you say, tell me how many clusters there are. Okay, the way all of those algorithms work is you have to say, suppose there's two clusters, which points belong to those two clusters? Suppose there's three clusters, which point belongs to those three clusters? So the choice of the number of clusters is a hyperparameter. You don't learn it from the data. The way these algorithms work is you have to say, I think there's two clusters, what are the assignments of points of samples to those clusters? So that's an example of a hyperparameter. You can just kind of eyeball the data and say, well, I think there's three clusters, but what if there was really two or four? So it's kind of similar to that problem with figuring out the number of galaxies in those images that we did before. So you could introduce bias in your results by setting these by hand. There's another approach that you can do, and that is just to use more data. So you've got your first data set, which is for training the model and learning the parameters. But you can always have, if you have lots and lots of data, you can now have a second independent data set that you use to study the choices of hyperparameters. So you kind of, in that sense, what happens is you now get kind of a hyper learning problem where you learn the parameters kind of on the inner loop, and then you have an outer loop where you learn the hyperparameters. And then probably there's going to be some things which are still fixed in that outer loop, and so you have hyperparameters, and so you can kind of continue this indefinitely. And one name that's often used in machine learning is cross-validation for this approach, where you kind of use a second data set that's not used for the training to validate your choices of hyperparameters. This is a very expensive thing to do. Machine learning is already very wasteful and makes inefficient use of your data. And now if you want to use, so now I'm saying you need even more data to learn something about your hyperparameters. Okay, but it's pretty important for when we use machine learning for scientific applications, because we always want to be avoiding biases, and when we have biases, we want to understand them. So it's pretty important to know what the important hyperparameters are. So I want to spend just a few minutes talking specifically about neural networks. I know you're going to get some more deeper dive in neural networks later on, but since neural networks are a really important part of the machine learning landscape, and it's really not obvious when you read about machine learning, read about neural networks, that these are really models. So I've been focusing, I say we've got the data, we've got the models. Okay, it's clear what the data is, but how is a machine learning a model? So how is a neural network a model? So first of all, I claim that models are basically something that it's controlled by all these numbers, these parameters. So the numbers in a neural network are known as weights and biases. So I got an illustration here of a simple neural network. So the neural network has the data coming in on the left. And so each node, each circle here is a node in this graph, just represents one number. So I have 1, 2, 3, 4, 5, 6, 7, 8. So this is a neural network for data that has 8 columns or features. So each one of the features, each time feeding the data to this model means that I'll take one row of my data set, which gives me 8 numbers, and I feed each one of those numbers in on the left-hand side. And then what the neural network, what it's doing internally is we've got these 8 numbers, and then they will flow through all the way through to at the end here. I'm in this example here, I have just 2 numbers coming out. So those are the predicted labels. And there's many different ways that many different graphs that you can build that go from the 8. I mean, the 8 is determined by your data, and the 2 is determined by the task that you're learning, right? So we've already set up a task where we have 8 numbers to describe each observation, and a prediction or a true label consists of 2 numbers. But there's many ways of building the internals. So for example, here I have 2 intermediate or hidden layers. And the first one has 4 nodes or numbers, and the second one has 3 nodes or numbers. So those choices are hyperparameters. And so the choice, the fact that we decided to have 2 hidden layers, that's a hyperparameter. Or sometimes it's better to think of them as hyper decisions, because they're kind of choices that you make. The data is not telling us that we need to have these 2 hidden layers. We just decide that's how I'm going to try and model my data. And the choice of having 4 and 3 for the number of hidden nodes, those are hyperparameters. You don't learn those from the data. If a neural network is a model, then it must have some simple mathematical, it must be describable in kind of mathematical terms. And that's true of neural networks. So, actually, neural networks are surprisingly very simple mathematically. The reason that they have such rich and complex behavior is because you take a very simple building block and you keep iterating on that building block to build up a much richer structure. But if we just focus on one of these internal numbers, so the one I've got my mouse on here, okay, so the number in that dot right there, that's X out. The number that's flowing out on this red line is X out. So where does that number come from? So it comes from all of the inputs, these 8 numbers here. That's the vector X in. And then how do we go from those 8 numbers to this one number? So X in is a vector, so we multiply it by a matrix, and the numbers in that matrix are what's known as the weights. And then we also add some offsets or biases, and so that's a vector. So because X is an 8-dimensional vector, so then there'll be 8 elements to this bias. And if we think of generating all 4 of these numbers at once from all 8 of these numbers, then you can think of W now as an 8x4 matrix of weight. So we basically just got a matrix, an 8x4 matrix, and an array or vector of length 4. So the things in green, those are our parameters. So a neural network has parameters, and internally, it's just doing linear algebra with those parameters. And that gives you some insight into why those GPUs, or graphical processing units, are so powerful and important for machine learning, because they were originally designed to very quickly render 3-dimensional scenes. So, and what's the math behind rendering 3-dimensional scenes? It's all matrix transformations and vectors. So it really is all linear algebra. And so that's why that hardware was perfectly suited for working with neural networks. So everything inside the parentheses here is just purely linear algebra. I've written it also down here on the bottom, just in Python. So we have W, our parameter, our NumPy array of weight parameters. We just dot it with the input array, and then we add the bias array. And so what you get out from here is just numbers, and then we wrap those numbers with this thing here, which I call phi, which is known in neural networks as the activation function. And although everything inside here is linear, the activation function, and this is really key to why neural networks are so expressive, the activation function has to be nonlinear. And it's that nonlinearity which really allows neural networks to just building from this very simple building block. That's what allowed neural networks to be extremely expressive, that small amount of nonlinearity. And the activation function that's used most commonly is actually the simplest possible nonlinearity. So it's something called ReLU, which I've just written here as a one-line function in Python using a lambda function. What ReLU is it's just it just takes it's basically 2 completely linear sections. When S is positive, then it's just y equals x, a straight line with slope 1. When S is negative, it's 0. Okay, so you have two flat lines that join at a kink at the origin. So the nonlinearity is only right at the origin, and that's sufficient to get all the richness of a neural network. Because you'll be talking more about neural networks later on, but I just want you to kind of just look under the hood and see that a neural network really is a model in the same way as all of the other models that we've been talking about. The parameters are the weights and the biases, these things in green, which are associated. There's a different set of weights and biases for each one of these layers, so they add up quickly. And then the hyperparameters are things like the number of internal or hidden layers, the number of nodes in each layer, the choice of activation function, whether you use ReLU or there's a whole bunch of different. Anything that's nonlinear here will give you some sort of useful learning. So another way on this theme of neural networks are models. So one of the things that's kind of surprising about neural networks is that they're often used very successfully when the number of parameters, the total size of those weight and bias arrays can actually be larger than the number of rows and columns in our data set. Okay, so that seems kind of paradoxical. It's like trying to solve a system of 10 equations with 100 unknowns. Okay, it's just like you can't do that mathematically, right? Well, but it turns out you can, and the way you do that is using there's different kind of terminology for it, but it's often in machine learning. It's also the way that this is possible. The general approach is something that's known as regularization, and in the more statistical language, we would call that priors. We'll talk a lot more about priors starting tomorrow. Now, let me just give you just one example of a regularization technique that's really important for training neural networks, which have more parameters than the amount of data. So what I'm showing here is the optimization. So this is basically what the function that's plotted here is the loss function, or the function that says how well our model is predicting the data. How it's a single number that says how well our model has learned the data. And this is a very oversimplified example where there's just two parameters. Okay, so that's why we can represent it just as a two-dimensional image like this. And so we start out at some point up here with just an arbitrary set of parameters, and we just walk downhill in this loss function until we get to the minimum. Okay, so learning fundamentally is really just optimization. Okay, we've got a bunch of parameters, and we're just going to iteratively, each one of these steps with the dots is one iteration. We're going to iteratively improve the parameters we've used. So we're adjusting the knobs until we get to a minimum of the loss function. And so that's sort of a classical numerical algorithm. Optimization has been known for how to do that for 100 years. And there's algorithms that like in SciPy Optimize, for example, that are very efficient at doing this. Okay, but the way that in machine learning we actually optimize the path that we follow to get to this minimum, it doesn't look like this really nice, smooth, efficient path. Generally, what we do in machine learning is we take this sort of drunken path which looks pretty a bit chaotic, and it does eventually get there. It needs a lot more steps. And so what's going on here? So this is an example of regularization. And what we're doing, I mean, there's different ways of accomplishing this, but the general idea, though, is that in order to calculate the loss function at each step, instead of using all the data, what we do is we just use a random subset of the data each time. So what that means is that we're effectively kind of just changing the problem. We're shuffling the data or randomizing the data. So we're changing the goal, the task subtly on each iteration. And that's what causes it to kind of wander back and forth like this. But it actually serves a very useful function because it prevents the model from just memorizing the training data, because every time it sees the data, it sees a slightly different version, like a random permutation or a random subset of the data. So it never really gets to see the whole data all the same over and over. It sees like random different perturbations to the data every time. And so the real danger, if you have more parameters than you have data in your your spreadsheet, then there's a real danger of what's called overfitting, which just means that the model is just going to memorize your data, but it's only going to memorize the training data. So that's going to be useless for generalizing data that it hasn't seen before. And so by introducing this randomness or stochasticity, then this is a type of regularization that prevents the model from overtraining, and it then performs much better on data that it hasn't seen before. So that's kind of one important example of regularization. This process here, the very smooth process that's implemented in SciP optimized, that's called gradient descent. Gradient is just another word for slope. So you just basically, it's just like a ball rolling downhill. You start the ball up here. You calculate local partial derivatives to figure out what the downhill direction is, and you just take these downhill steps. When you add this randomness, so now this is called stochastic gradient descent, or SGD. So you'll see that term a lot once you start working with frameworks like PyTorch or TensorFlow. That's kind of a standard way to optimize the loss function. To do the learning is using stochastic gradient descent. And as I said, in the language of statistics, we usually think of this in terms of invoking priors on the parameters. So we'll look more at that perspective tomorrow. Another consideration with neural networks, in general, there's far too many hyperparameters to optimize in practice. And what this means is that progress in machine learning with neural networks, or kind of in deep learning, tends to progress is not smooth. There's so many hyperparameters that there's not really any efficient way to explore and figure out the best settings for all those hyperparameters. So this graph over here shows you the history on a particular competition that's held every year. So this is what's known as the ImageNet competition. It's a large set of images, and the images have been labeled by humans as to what objects they contain in them. So there's a list of 1,000 objects, and each image is labeled by which one of those 1,000 objects the image contains. And so the task in this somewhat artificial competition is, given an image, just to predict what the object is in the image. So like sailboat or dog or cat. In fact, for historical reasons, when they chose those 1,000 categories, I think there's something like 100 different breeds of dogs in those categories. So algorithms that do well on this ImageNet competition are actually much better identifying different types of dogs than most humans. So what this graph is showing is in 2011, this was there was 4 entries in the competition. These are actually the best 4. And so, the best one was it had an error rate of about 25%, and the 4th place one was 50%. So really not very good. And then the next year, there was an improvement by a factor of 2. Okay, so this dramatic improvement. And in fact, most people, think of this entry in this competition by Kirkby in 2012 as kind of the moment that kind of the modern deep learning revolution began, because this was a huge breakthrough, this factor of 2. But what happened? So basically, it was someone came up with a new idea, a new algorithm, and then what the idea was convolutional neural networks. So you'll probably hear more about that later. So no one before had really been using convolutional neural networks. They've all been using so-called dense neural networks. And then all of a sudden, someone came up with that idea. And then if we look in the subsequent years, then everyone is basically now using convolutional neural networks, and then people are kind of clustered together. And so because there's so many, there's such a large space of possible ways of constructing an algorithm, or even just working within neural networks. So there's just kind of an infinite number of hyperparameter choices to make. So the progress in deep learning is not really smooth. There's not like a kind of a robust, reliable way to just make steady progress year by year. It really just requires on someone having a crazy idea, trying it, and most of those won't work, but then sometimes they do work. So people often refer to this jokingly, or maybe depressingly, as grad student descent. So instead of gradient descent, grad student descent, what that means is that the way you make progress in deep neural network architectures is you set 100 graduate students, each working on a different approach, and then maybe one or two of them will find something that works, and then everyone in the community starts using that algorithm that they hit on. So that's how the progress has really been. It's not kind of a smooth logical progression. It's more sort of if someone hits on an idea and it works, and then everyone starts doing that. This line right here, the dashed horizontal line, that's the human performance. So back in 2015, then there were about half of the entries were getting better than human performance. And by 2016, all of the algorithms are doing better than humans in classifying these labels. Remember I said earlier, it's pretty hard to do much better than human performance if your training data was labeled by humans. So at that point, and now you need to come up with a different way of labeling your data to get any better than human performance. Okay, so I'm going to stop there. There's a bit more in these slides, but we'll pick that up tomorrow morning because I want to stay on time. Let me stop sharing. And if anyone has questions now, I'm happy to take those. And remember, your homework for tomorrow is to come up with a data set that you're going to work with tomorrow. So instructions for that were on slide 60.
So a question that some students had earlier in the morning was if they could be working at Google Colab or Google Collaboratory. I think that's the name.
Yeah, I think that's fine. Yeah. So one of the nice things about Collaboratory is that you can try a GPU on Collaboratory. So, but nothing we're going to be doing is going to need a GPU. Also, it can be, some of the packages, machine learning frameworks like TensorFlow can be a little tricky to install. So it's nice that they actually, Collaboratory has those things pre-installed. So.
So am I right assuming that if they have questions, they can write to you in the Slack channel for the session? I think that you already set the channel for the session, probably not. I think it's a general MACSS, but I could also make another specific channel for the.
I think you made one which was called Bayesian Inference and Machine Learning.
Yeah, that one.
Yeah,
exactly.
Yeah, so feel free to post questions there. That's the channel. Okay, yeah, and if you have questions about, you're not sure what what data set to pick, then you can also just message me directly. So.
Is there any question from students? I think before we go into break, we have time for a couple of questions.
I have a quick question.
Yes, please go ahead.
About when you say that we need like a way to measure how similar to rows are, about a metric set.
Yeah.
That's part of the model, like the way we define how to measure similarity between the data.
No, I would say it's really part of the data. So often it's important to pre-process your data in a way that there is, I mean, ideally you want just a Euclidean norm between two rows to be a sensible measure of the distance. So if you have features which are of different different units, then you think about how to put them in the same units. So for example, if you have length and time, then maybe multiplying the time by speed of light or some velocity would put everything in length units, and that might be a way to do that. So, but like the clustering, unsupervised clustering algorithms I was mentioning earlier. So that in order to cluster, you have to have some notion of 2 points. How close are they? How close are they together? And so yes, it's a lot of algorithms internally assume that you can just take Euclidean distance to measure the distance between things. But if you had one feature which was in microns, and then let's say you have 2 features in micron, and then you change one of them to be in meters. So now you've changed the numbers that are in your table, by a large factor, but you haven't really changed anything about your data, but it would completely change the Euclidean norm. So.
Okay, so in general, we have to convert to everything to its, so it can be used Euclidean norm properly.
Ideally, yes, yeah.
Okay.
But you don't need to do that for tomorrow. But I mean, that's as often as you spend more time with the data set, you kind of becomes you figure out the best ways to pre-process the data. So another example is we often use images as our data in astronomy, but the dynamic range of an image is huge, because you have everything from the sky level, and then you have really bright stars, which can be many orders of magnitude brighter than the faint galaxies we're interested in. And machine learning algorithms generally don't work well when there's a really large dynamic range. So you have to think about how to kind of compress that range. One simple thing is just to take the log of the flux. So that's one approach. It doesn't work so well if the data is already being sky subtracted, because then you'll actually have some pixels with negative flux, so you don't want to take the log of a negative number. But those are kind of the things you need to think about.
Yeah, thank you.
I think Oleg has another question.
Yes. Hi, David. I was wondering regarding the features. What if you don't know where the features come from? What if you have some data set that you really don't have much information of the nature of the features? How would you start to categorize what is important in that data set and how to select what to input into a model?
Yeah. Okay. Well. So we'll look at some examples of that tomorrow. But generally, I think you first wanted to start with kind of classifying the features. Is this a continuous feature or a discrete feature, categorical feature? You generally want to have some idea of which features are more important or less important. And you can only answer that question if you have a particular task that you're trying to solve. So it's not just the data, but it's what's the question you're trying to answer. For certain tasks, there may be some features which have essentially the same information, and so they're really not adding. You could just delete one of those columns, and you wouldn't really make any difference. So I mean, those are the kind of questions that you want to start looking at, like which of the columns, which of the features that actually have the most information. And often a really, the straightforward way of answering that question is just with, for example, PCA, so principal component analysis. You don't need to use any fancy neural networks, just get a feel for how much information each of your features carries individually. So, but again, you can only answer that question given a particular task. So.
Thank you for the answer.
I think there is time for one more question, and we need to go into the break. So, Luz Angela.
Thank you. I'm wondering if you have any insight on how to prepare the data if you don't have any real knowledge of I don't know, correlations between the variables. I mean, it's easy to do it if that's physical, or if you have some insight on the nature of these variables. But if it's something, I don't know, like I choose a data set related to happiness around the world. So
yeah.
Do you have any insight on how to prepare the data if you don't have any idea on how to get the data, or if there's any correlation between the data set?
Yeah, right. So that's a good question. So, first of all, if it's continuous data, then something that works surprisingly well is just to measure the mean and the standard deviation of the values, and then to basically put it into a normalized form. So you would just subtract the mean, so that's going to have the same units, and then you divide by the standard deviation, which will also have the same units. And so in that ratio, so you basically take x minus mu divided by sigma, and so that is going to become dimensionless, and so that's good, because as long as all your features are dimensionless, then at least Euclidean norm makes sense mathematically. And it also makes sure that everything, all of the values of that now standardized feature, they're all going to be close to 0, and they're not, the spread from 0 is going to be on the order of 1. So that's always, like, if you really don't know anything about a continuous feature, that's always a good idea to do that. And then in terms of discovering correlations, so we'll look at some examples tomorrow on the data sets that you guys choose to kind of what we're talking about, sort of the exploratory phase of the data analysis. So kind of more the data science, like just how do you discover kind of what the relationships are between different features in your data. And of course, that's what's interesting about your data is the relationships between features. If all of your features are completely uncorrelated with each other, it's not a very interesting data set. I mean, that's basically like, coin tosses or dice rolls. Okay, so which are often the examples that we use in statistics, but they're not at all interesting. Data is only interesting because of the correlations between features. So. Okay, well, thank you for the question.
Thank you very much. So thank you. I think we are going to close up here, and then we will meet again with David tomorrow morning. And everyone feel free now to go to your coffee break. Remember, there is a link for the break on WonderMe. I think Mariana already posted in the chat. So see you there. And we will come back to this main room here for the second part for the projects, and we will give you instructions there. If you haven't filled out the form for the projects, please do it as soon as possible. Thank you, David. Bye. And just so that you know, we are going to close momentarily this Zoom, and we will open it again almost immediately, but this will throw you out. Thank you. Luis, so I think we can close and reopen it for checking the breakout.